and for his style of writing, which, as you can see, is described as crisp, captivating, and illuminating. We're really, really, really fortunate to have him here today. So this is Professor Hans Christian von Baeyer.
Thank you very much, especially for inviting me here. I am particularly grateful that I get to answer Maria, who essentially, in her beautiful talk, suggested that all physicists should be eliminated. So I'm glad that I got the last word, so perhaps I can convince you that not all of us immediately have to leave the planet. Most of what I'm going to say today is derived from my book, Cubism, and I also have to thank you very much for increasing the sales of my book for this year by about 75%. So by handing out all these copies, I think your daughter said you're throwing out books, and I'm very grateful because that's what they're written for, throwing them out to the public. I am going to talk about Cubism, which is pronounced like the art historical period, but has nothing to do with it. Cubism also, the quantum cubism has the interesting characteristic of being written in a strange font. It's not capitals and it's not lowercase. Does anybody know what that font is called in which cubism is spelled? Most people don't know that. It's called camel case. Not uppercase, not lowercase, but camel case, like the animal, because it has humps in it, like FedEx. And nowadays, you can't open a new company without writing its name or its logo in camel case. So that was one of the things we wanted to do with this book. Anyway, Cubism, which is short for quantum Bayesianism, is an interpretation of quantum mechanics. And what that means is it doesn't change any of the quantum mechanics that we've heard about today that underlies quantum computing and that underlies all the electronics that we carry in our pockets, which is probably one of the most successful scientific theories in the history of the world. Cubism does not change any of those things. So don't wait for me to come up with new wrinkles on the technical science of quantum mechanics. It's an interpretation, which means it looks at the terms that are used and interprets them differently, endows them with new meaning. Now, why would you want to do such a thing if this quantum mechanics is so eminently successful? Well, first of all, because for 100 years, philosophers and mathematicians and physicists have debated about what all this is about, what quantum mechanics means. And that's rather disgraceful because it's not true for astronomy or chemistry or most other sciences that we use quantum mechanics and we don't really know what we're talking about. More generally, what we would really like to find out is what is quantum mechanics trying to tell us about the real world? An example was in Eric's talk when he mentioned that teleportation is based on entanglement, and he sort of equated that with action at a distance, with spooky action at a distance, with non-locality. Well, cubists don't believe that, and there are other people who don't believe that. And we owe it to our students not to take such things for granted if they are in fact questionable or debatable. So we will come back to that. A minor example from Maria's wonderful talk was that she wants to replace talk of electrons and superconductors and things like that by vectors. And she says a qubit is a vector. Well, a qubit is not a vector. According to the originators of the phrase, a qubit is a physical object, like a switch. A Bloch sphere is a representation of the state. That's a big word, and so you want to shorten it, but it's a representation of the state of such a switch. So while it is very admirable that she wants to clarify what she's talking about and she wants to talk about vectors, that's fine, but she shouldn't really call them qubits. Qubits, and I will also come back to that a little bit later, that qubits are perfectly satisfying representations of states of physical objects, but they are not the same thing because an electron, for example, has mass and has charge, and maybe it has color, I don't know, whereas a vector or even a Bloch sphere or a vector in a Bloch sphere hasn't any of those things. So we shouldn't give young students the impression that we know all about electrons. They are vectors. Well, they're not. So that's what the reason, these are some of the reasons for going into the kind of discussion that I'm about to go into. We've been told today several times, and it's clear and it's very exciting, that we're beginning this era of quantum computing. And new questions arise. One of them this morning was alluded to, the question of quantum supremacy, which means the question of whether classical calculations are faster or slower than quantum calculations, and under what circumstances. Well, are they mainly, is quantum supremacy over classical computers, is that mainly due to superposition or entanglement? Well, superposition and entanglement are difficult concepts. They are tricky ideas that come from quantum mechanics. So we have to study what that means at the fundamental level. And we will see over and over again in the question of interpretations of quantum mechanics that we're dealing with two things. We're talking about classical language, particles, waves, energy, things like that were talked about in the 19th century, and modern language, which has in it wave function and state vector, entanglement, superposition, things like that. And there's an interplay between these. The attempt is to take these newfangled equations and express them somehow in words that have more intuitive appeal, like a particle. We all know what that is, and we know what a wave is, and we sort of know what energy is. So we're trying to interpret the quantum mechanical wave function in those terms. And that is a dicey undertaking. It's difficult. And there are many, many attempts to solve it. So how did we get into this muddle in the first place, that we have, on the one hand, a classical language that appeals to our intuition that we learn every day in our homes, and on the other hand, we have this new language which is perhaps incompatible or somehow badly represented by the old language. Well, we got into this muddle strictly through what the ultimate test of science is experimentation. And it's a wonderful irony that J.J. Thomson received a Nobel Prize, and there's obscured here, a Nobel medal, because he showed that electrons behave like golf balls when they are deflected, not in the gravitational field like golf balls, but by electric and magnetic fields. Okay, so electrons are like particles. Well, his son, G.B. Thomson, his son, 25 years later, got a Nobel Prize for showing that electrons spread out in space the way waves spread out on a lake. I think that's a wonderful irony that both of these, father and son, got a Nobel Prize, one for showing that electrons are waves and the other that electrons are particles. Well, this caused a ruckus. It began the era of quantum weirdness, which in the technical language is called wave-particle duality. And magazines and newspapers and radios talked about wave-particle duality, and the popular imagination went wild. Not only the popular imagination, but I first came across quantum mechanics as a boy in George Gamow's wonderful book, Mr. Tompkins in Wonderland. He never got a Nobel Prize, but he basically predicted the Big Bang, which I think is an amazing thing to do. And he wrote these whimsical books about physics, and one of them was about quantum weirdness, one of them was about wave-particle duality, and this is how he imagined it. He talked about quantum billiards, and there's this white ball, and it comes shooting down just like a ball should, and then it rebounds, or rather the black one hits the white one, and the white one went off in all directions. This is supposed to be an illustration of something that behaves both as a particle and as a wave that goes off in all directions. Well, this is not a very successful analogy and didn't help me very much, any more than the words were invented for wave-particle duality. For example, one physicist suggested that electrons are wavicles. Well, I think that's a very ugly word, and it doesn't get me anywhere. An electron is, in Latin, sui generis. An electron is an electron. We may represent it by a vector or a Bloch sphere, but an electron is an electron. It is certainly not a wavicle. Well, of course, Einstein got there first. He, fully 16 years before quantum mechanics was even thought about, he said, "I believe that the next phase in the development of theoretical physics will bring us a theory of light that can be considered a fusion of the wave and particle theories." He knew that intuitively. He wasn't very happy when 16 years later quantum mechanics came along. That didn't fully satisfy him. But he foresaw that that was going to be important. So that is how the muddle started. And he said it of light, and shortly thereafter, as we have seen, the two Thomsons showed that the same had to happen for the theory of matter, for actual particles like electrons and atoms and nuclei and things like that. So how does quantum mechanics come about? What's the essence of what happened? Well, what happened was that the inventors of quantum mechanics, basically Schrödinger and Heisenberg, realized that they had to try somehow to stop describing things as they really are. All through the 19th century, when people talked about atoms and electrons and planets and the world, they were talking about it as though they were describing what is really there. That's what science is supposed to be about. And they said it doesn't work. The wave-particle duality shows that it doesn't work. So instead, let's just find a mathematical expression which can reproduce the wavy behavior and also the grainy behavior, as Einstein had predicted, and that was then called the Schrödinger wave function. But that does not mean that is the electron. This is this is simply a mathematical invention which can reproduce both particle behavior and wavy behavior. That's the point of the Schrödinger equation. As Werner Heisenberg, who was really a year before Schrödinger, said that the conception of objective reality, that we're really describing the world as it is, has evaporated into the transparent clarity of mathematics that represents no longer the behavior of actual particles, but rather our knowledge of this behavior, because we have this wave function so we can figure out what this behavior is, but the electron is still over there and is out of our reach. So instead of the Bohr atom, which is a very tactile and powerful image that we teach all third graders, now what we're faced with is these strange symbols. But if we manipulate those strange symbols, then we get back the behavior of the atom. But the atom, the visualizable atom, has to make room and make room for this totally mathematical object. Or I could have, up there, I could have put the Bloch sphere too, or the vector, as Maria would say, which is visualizable and we can imagine it. But instead of that, we have mathematical equations. Well, that idea that you have to be careful about that kind of thing is was in the 1930s when all this happened, all this quantum mechanics was invented. That idea was current among other people, among philosophers and artists. For example, the philosopher Korzybski says, the map is not the territory. Well, that's very true. I find that especially when I travel with my daughter, she thinks that the map is the territory and she obeys the Google map and she goes, you know, down the wrong way because the map is not the territory. If you look out the window, you'll see it's a one-way street in the opposite direction. You just have to be careful not to confuse the map with the territory. And the artist McGrady painted a painting and he says, this is not a pipe. No, it's not. You can't smoke it. It represents a pipe. So maybe, just maybe, the problem with quantum weirdness lies with confusing the map with the territory. Maybe it's the wave function that's at fault and not the electron. Of course, once you make a new assumption like that, when you throw away a lot of the properties of the actual thing, you're compromising. You're no longer talking about the actual thing, so something has to give way. And what gave way was that it was no longer the case that you can describe an electron in an atom the way you describe the moon going around the Earth, or the way you can describe a water wave. Once you give its amplitude, its wavelength, and the way it bounces off boundaries, you've got complete control over the wave. That's no longer possible. All we can do is get the probability of finding many possible outcomes. So there was a compromise in what Heisenberg and Schrödinger had invented. Now, I said only in quotation marks because the actual probability, once you compare it with huge data sets, is exquisitely correct. Quantum mechanics is good to 10 decimal places, or sometimes 12 or 14. So the only is that's a pretty big only, but it's only a probability. You can't say that the electron is going around the atom. As a matter of fact, in my book, I have a section about attacking the Bohr atom. The Bohr atom is taught in every school in the world, and every child who's not particularly in physics thinks that that's what an atom is, and it's completely wrong. And the inventor of the Bohr atom, Bohr, 6 years after he invented it, had to repudiate it because it's completely wrong. For example, the electrons are always, in the Bohr atom, are always around like that, away from the nucleus, the way the moon never crashes into the Earth. But the wave function of the electron going around a hydrogen atom has its maximum where? In the middle, on the nucleus, right in the middle. Anyway, so I go into a big spiel in my book about how horrible this symbol is. It's sort of like a highway sign that has a logo for the airport, which is a Wright Flyer, you know, something like that. Anyway, so the compromise was the probability instead of the certainty. So was quantum weirdness gone now that we had quantum mechanics, which is a nice compromise? Well, it came right back in a new guise. Quantum weirdness returned with a vengeance. The problem, the quantum weirdness that particularly induced me to go in a different direction, namely cubism, is this wave function collapse, which was talked about a lot today, also called the reduction of the wave function or the quantum jump or something like that, is what bothered me particularly. That's a mystery. First of all, instead of having one equation that describes the path of a golf ball, which I've been teaching my freshman mechanics class, you know, for 50 years, there are two different things. It takes two completely different mechanisms to describe an electron going around an atom, or I should say an electron in an atom. First, there's the smooth evolution of the wave function, and that's what we saw all day today, the smooth evolution through gates and things like that of a wave function. And then comes the so-called collapse of the wave function, where suddenly it collapses from being spread out everywhere to a certainty where the electron actually is. And that second quantum jump, that collapse of the wave function, first of all, is not described by any equation. It just happens. You just have to add it. You calculate your wave function, and then when you observe this thing, the wave function collapses. Why did it do that? How did it do it? Especially, how fast did it do it? Well, it does it instantaneously. And of course, Einstein told us that that's bad. You don't instantaneously do anything in real world. You can do it on paper. You can do it with a wave function. You can do it with your representation. There's nothing wrong with that. But what is it really about? And what bothered me was that there are two laws of motion. Von Neumann introduced that way of speaking about quantum mechanics, that there are two completely different laws of motion which have nothing to do with each other, and the second one is unmotivated. It just works. You've got to go from a wave function, which is everywhere, to the certainty of knowing that a qubit is 1 or a qubit is 0 or something like that. I just made the mistake. I called the vector a qubit. What I meant was ... Okay, anyway, so the second description of how a wave function behaves violates the relativistic limit. And ever since then, ever since 1925, 1926, there have been many workarounds about this problem. The many worlds interpretation of quantum mechanics, which is very popular, does away with the quantum collapse. And it says there's this wave function which just gets bigger and bigger all the time and never collapses. So when somebody observes something, then the wave function bifurcates into two branches, in one of which the electron is up and the other one the electron is down. And we happen to only live in one, so we only think it goes into one, and the other one gets lost. But this was a pretty drastic thing. The only thing you have to pay for believing in the many worlds interpretation is that you have to deal with infinite wave functions, which infinitely fast split into an infinite number of branches, all of which you can't see except your own. And I just don't like that. I mean, that's not philosophically very nice. Another one that Einstein believed was a guiding wave. He did the opposite. He said you have both particles and you have the wave, and the wave guides the particle. That's why it's called a guiding wave, the way an electric field guides an electron. But that is not very popular anymore, because that guiding wave is some kind of a quantum field, and nobody knows what that is. Then there was one which was spontaneous collapse, which says that, which also still has adherents, which says that any wave function collapses spontaneously. It just collapses, boom, like that, and nobody knows why. But it does it very rarely, and it does it fast when there are many particles involved. That's why we never see it. That's why we're not used to it. None of us have ever seen a wave function. Anyway, I'm making fun of them, but there are probably 12 interpretations of quantum mechanics. So quantum weirdness brought us the wave function collapse, and then it brought us the famous Schrödinger's cat, and I'm not going to talk about that, except to say that it doesn't help very much, because it all predicated on the idea that the atom in that little atomic device has to be in a state of being both decayed and not decayed. It has to. How do we know that? Because countless experiments have shown us that that's how atoms or nuclei behave. You can't describe them as though they were either decayed or entire. You have to describe them as a superposition. And then once you know that, then everything else follows, and the cat is both dead and alive. So all that, the purpose of the Schrödinger cat idea was to elevate the mystery of superposition into some image that we can understand, namely a cat that's both dead and alive at the same time. But you could do away with the cat and the hammer and the gas and all those things and still ask, what does it mean for a nucleus to be both decayed and not decayed at the same time? It's the same mystery. So it's simply a way of magnifying a problem that appears at the fundamental level. Well, before I said let's dig into these new quantum mysteries. I said that the wave function doesn't describe a specific outcome; it describes a probability. So here again we have this bifurcation of language. The wave function is a quantum mechanical idea, and probability was thought to be a classical concept. Everybody knows what probability is. Every captain of a football team knows that the probability of tossing a coin is 50% heads. So it was confidently thought that probability was just a normal term, and physicists didn't question it. They argued about wave functions and state vectors and entanglements for 100 years, but they didn't argue about these other things because everybody knew what they were. Well, what happened with cubism at the beginning of this century was that probability word was bumped up to here, that it's just as problematic as wave function and state vector and entanglement and things like that. That's what cubism is about. So, last year, Chris Fuchs, who is one of the main author of cubism, and his student Stacy, he says the problem with physicists and probability was, I should say, that when one has vast heaps of data, like atomic physicists have and solid-state physicists have, pretty much any even half-baked interpretation of probability is good enough to scrape by. So that's why they thought, this was okay. Yeah, we all know what probability is. It's you teach it in grade school. It is not until we push further into matters of principle that mediocrity begins to pose a real hazard, and that's what happened. So we have to talk about probability. We'll pretend that probability is not what we all think it is and think about it little. Well, there are two definitions. Everybody knows the conventional probability, which actually is the newer one of the two. That's the 20th century version, and it's favorable cases over all cases, the number of heads divided by the total number of tosses. And it is supposed to be measurable. You just throw a lot of times and you find what the probability is, so it's objective. And physicists said, yeah, that's nice, it's objective. And then there's the older definition, 18th century, which is now making a tremendous comeback, called Bayesian probability. And it is a real number between 0 and 1, as all probabilities have to be, expressing an agent's degree of belief, and the hair should stand up in the back of your neck. Here's this professor of physics talking about degrees of belief in the likelihood that an event will happen or that a proposition is true. It is subjective. And many of my colleagues want to shoot me for saying that. Okay, what's wrong with frequentism? Well, what's the definition, the meaning of a probability of a coin toss? In a large number of tosses, heads comes up about half the time. If that happens, then the probability of heads is approximately a half. That's very objective. I have my children do that for the heck of it. But mathematicians don't really like words like large and about and approximately. That won't do. So they clean it up. In an infinite number of tosses, head comes up half the time, and the probability is a half. Unfortunately, nobody has ever done that. That's not objective. It's not a verifiable fact. Now, I'm not saying it's not going to happen, but it is not an objective definition. So, in a way, in this case, frequentists fool themselves in saying we're so objective. Another trouble. Sorry, I went the wrong way. Another trouble with frequentism is that a single case probability is completely meaningless. When you say this meat is probably bad, then you can't very well do an infinite number or even a large number of experiments. Or when Obama said the probability of the bin Laden raid succeeding is 55% and therefore we're going ahead, that is not a frequentist definition. It is not the case of taking the favorable cases where bin Laden is taken out and dividing it by all the cases. You haven't even done it yet. So for single cases, frequentism is useless. So instead, we go back to Reverend Thomas Bayes. He didn't really invent modern Bayesian probability, but he started it. And it is called Bayesian probability. The mathematics of it was really elaborated in the 19th century by French astronomers, but that's the guy whose Bayesian probability is named after. And all my beautiful illustrations are obscured by your symbol up there. Anyway, this person is scratching his head. Bayesian probability requires you to define a number expressing an agent's degree of belief. How do you do that? My degree of belief is 0.2975. How do you do that? Well, Bayesians have come up with it. They say it has to do with betting, and that's where probability started in the first place 2,000 years ago, gambling and betting. An agent assigns a probability p, a number, between 0 and 1 to an event if she's willing to bet up to P dollars for the chance of a return of $1. She buys a ticket for this $1 if the event E occurs. So for example, you would pay 50 cents for a $1 chance on a coin toss. If you paid $1.10, that would be really stupid. If you paid a negative number, it would be stupid. Other examples come to mind. I would pay at most $1. I would pay 99 cents or $1 for a chance that the sun will rise tomorrow, because I think it'll happen. If I got a $1 ticket for 99 cents, I'd make a cent for sure. So that would be good. So that puts a number on it. What would you give for a $1 chance that it's snowing here in Portland tonight? I don't know. I'd give maybe a couple of cents, you know, not much more, because I don't think it's a very likely thing. So now we have a number. Each person has to define it for himself or herself. The Bayesianism that I'm talking about is one person calculated that there are 4,300 versions of Bayesian probability. Well, that's maybe a little exaggerated, but there are people who say, well, Bayesianism can be made objective and so on. Okay, that's fine. I'm talking about subjective Bayesian probability. I just didn't want to say the word all the time. I'm talking about the subjective, personal version of Bayesian probability. That's the word that gets abbreviated by cubism. And such a probability depends on information that you have and on your opinions. It has a smell of relativity to it, because Einstein already told us, well, you can't ask, how fast is that plane going? That's a nonsense question. It depends who's asking, you know. The pilot would say 0 because he's sitting in it, and the person on the ground would say 200 miles an hour because he's watching it. So speed is already relative, not to a person, but to a person's frame of reference. So why not probability? Probability is relative to an observer. I have a probability, and if I make a bet with you and I happen to think you're cheating, then I'm going to bet differently from if I don't think you're cheating. So my probability assessment for making a bet with somebody depends on my own observations, on my information. Bayesian probability is applicable to unique events, because you're saying Obama bet on the raid. Most famous advantage of Bayesian probability is that it can be updated, that when you get new information, you change the probability. And you know, that's a very scientific thing to do. Scientists are always making guesses of what's going to happen, and then they get new information and they change it. And for simple cases, there's even a law or rule or theorem, which is a mathematical law and very, very much applied in modern engineering. It's not useful in all circumstances, because not all probabilities can be so simply determined, but this Bayes' law has become, in the last 20 or 30 years, very, very popular. Bayesianism, I claim, is more general than frequentism, that it's okay for a Bayesian to take a frequentist probability and use it to make his or her own probability assessment, but not the other way around. Well, not the other way around is obvious. If I just guess at something, then a frequentist can't use that. But if, for example, if a frequentist determines the probability of a coin toss to be 1/2, they've determined, even for a single throw, they have determined the value of P, but they can't define, I've gone through that, they can't define the probability that way, because the one single throw of a coin has nothing to do with somebody else making a series of coin tosses. It's a big It's a big extrapolation. So what I'm trying to say is that a frequentist can determine a value of p that a Bayesian is allowed to use. And that's nice because now the Bayesian can adopt all of frequentist probability and incorporate it in his own worldview, and it can't work the other way around. So you don't have to throw away those simple cases where, which folks call the simple-minded cases where you have a lot of data. You can work those into Bayesian probability without any trouble at all. Okay, nowadays we see Bayesian probability everywhere. The idea of quantum Bayesianism is to put together two existing theories, quantum physics since 1925, and Bayesian statistics, Bayesian probability, which was originated in the 18th century. And you mash them together and you get quantum Bayesianism, which is such a big word that cubism was invented. I have to say that cubism, since it started in 2001 with one short little paper, has morphed, and it is not quite the same. So quantum Bayesianism is not quite the same as cubism. Cubism is more evolved, is more sophisticated, but I'm not making a distinction today. By 2010, cubism was included in lists of alternative interpretations of the kind that I alluded to earlier. And then a little bit later, I started with others to, excuse me, popularize. Oh, here's some water. No, it's empty. Okay. Wrong Bayesian probability assignment on my part. Okay, so popularization begins, and that's when I started with this book. So cubism is a new phenomenon. This is a demonstration that Bayesianism is really here. You see that this list goes way up and has all sorts of other things in it that I mentioned, but when you get down to 2010, you actually come to this, and these are two of the co-authors of the original. Thank you very much. These are two of the original co-authors of the original paper. So this is from Wikipedia, and actually that's a pretty good article, strangely. Cubism is no longer regarded as complete lunacy. So this is Chris Fuchs. He's a professor at UMass, and I have worked with him for 20 years, and he's a very outspoken and friendly guy. For me, the big revelation was that wave function collapse just collapsed. The problem went away. The wave function is the prior probability to find an electron at a certain spot, or the prior probability of any observation that you invent, or you read it in a book, or somebody else told you. And then you make a measurement that gives you new information, and then you update your probability, and therefore you update your wave function. So, of course, it's a different wave function because you have new information now. You know, so what's the big deal? A nice example is if I have a picture of my daughter, and my wife and I are standing at the airport, and I cut it in two without looking at it, and I give her half, and I put half in my pocket, and I fly off to Portland. And she knows with 50% probability that she has the legs of my daughter in her pocket, and I have the head of or the other way around. And then, as soon as I look at my picture, instantly I know what she has in her pocket. Instantly, her probability for me changes, but it doesn't change for her. She's still standing at the airport and she has no idea. That's a classical example of updating with new information to collapse a prior to a different probability afterwards. So I was happy. Wave function collapse for me is no longer a problem. Schrödinger's cat, the purpose of the wave function is to tell the agent what she can reasonably expect. It says nothing whatsoever about what's going on in that box. You can't use quantum mechanics. You can't use that formula that you can use the formula that we have for the state of the atom, but you can't infer anything about what's going on in there until you open it, and then she knows, for example, that the probability of the cat being alive changes, but that's only what she expects to see. Any more than you can talk about the state of a qubit before in a computer science language, before it is observed, you can tell what it's doing. So anyway, it doesn't imply anything about cat being alive or dead. So that's another problem, say, solved. And then there's spooky action at a distance. That's Schrödinger's own expression, which I alluded to. And that comes into the picture, again, via Einstein. And he, together with two collaborators, Podolsky and Rosen, proved a theorem, basically, not really proved a theorem, but he indicated that quantum mechanics cannot survive together with two other assumptions, with locality and realism. Locality being no spooky action at a distance, meaning no, if I tickle the universe here, it'll feel it immediately over here. There's no such thing any more than there is Newtonian gravity, which when I shake something here on the moon, you'll feel it instantly. If you assume locality and at the same time realism, then you come into conflict with quantum mechanics. The realism, another way of saying realism is that the wave function describes a quantum system objectively, and I have the feeling that many people still secretly believe that, and I think many computer scientists and teachers of quantum computer science also deep down feel that the wave function describes a quantum system objectively, and that's not necessarily true. So this means that let's go back and say what happened to this EPR paper. Well, Einstein and his collaborators suggested it in 1935. Then experiments were performed. Even today, experiments are still being performed. Einstein believed in local realism. He believed in locality. That's why he invented general relativity, to get rid of the spooky action at a distance of Newton. He believed in local realism, and he certainly believed that the moon is there when nobody looks, that physics is supposed to describe the world without input from an actual observer. So he had to conclude that quantum mechanics is incomplete. He didn't want to say it's wrong. He said it's incomplete, and he hoped that something would be done. What's happening today? Well, everybody accepts quantum mechanics. If you have a cell phone, you have to believe in quantum mechanics. So you have to give up, according to this, either locality or realism. Take your choice. You have to give up one of them. There are still many people who believe in realism. They believe that they're describing the world the way it really is. And then they have to give up locality, and they believe in action at a distance, in spooky action at a distance, that the world is non-local, that if you do something here, something else happens there magically. The word magic was used. if you assume realism, you have to accept non-locality. Cubists don't give up realism. They change what realism means, and they reject non-locality. And I, as a cubist, believe that the world is local, that any kind of physical action has to occur at a very short distance, not at a large distance. If you choose realism, Alice's observation affects Bob's instantly and changes his probability assignment. If you choose locality, then their wave functions differ, and we've seen that cubism says that wave functions, being Bayesian, can differ. So don't take this picture as being an experiment or something very profound. This is sort of intuitively that Alice and Bob know that an electron is coming, and they know it's a wave, and they can write down the wave very accurately. And then she catches it. She's 100 miles away, and she catches it. Her wave function collapses, and he's 100 miles away. His doesn't. So you can make a choice. If you believe that the wave function that she has and he has is real, then hers, when she catches it, instantly affects Bob's. But if you don't believe that, then he has a different wave function. So everybody has a different wave function. I won't go into this. I'll say that cubists believe that the world is real. They're sometimes accused of being idealists or narcissists or solipsists or something like that, who don't believe that there is a real world out there. Cubists, I mean, I really believe you guys are out there, so cubists are normal people. They don't define, sorry. They believe the world is out there, but they don't believe that the wave function or quantum mechanics describes the actuality of what's out there. It's a representation that has good properties, but it's not, it is not the real thing, and it is relative. David Merman at Cornell, who became a cubist late in life, he says cubism is local because what it's about is correlations that take place in everybody's head. I mean, what do I know about quantum mechanics? What I know about quantum mechanics takes place in my head. Even if I do an experiment and I observe something, it's all in my head. It's all local here. And somebody else has something else in their head. So cubism is manifestly local. So you say, okay, great. The problems of wave function collapse, Schrödinger's cat, action at a distance are all resolved by cubism. So then people complain and say, well, everybody in this room has a different wave function. How can you do physics? You know, this is crazy. It's just, you know, if every one of us had a different wave function for an experiment, how could you even do science? Well, it's because cubism goes beyond just physics. John Bell says it goes beyond piddling pointer readings, but everything else that I experience, the books I read, the lectures I listen to, the conversations I have, the experiments I do, all those go into my wave function. And that's true, you know, if I did an electron experiment, I wouldn't go there and measure the wave function. I would look in books and ask my friends and do some research and Google it and so on, and finally I'd come up with a believable wave function. And that would be my prior, and that has to be logically consistent with everything else I know, and then I make the measurements. So the reason we overlap the knowledge of wave functions, for example, and of our knowledge of the world, is because we overlap, because we talk to each other, and we exchange information. If everybody in the world was completely isolated in a locked room, there wouldn't be any science either. You know, you've got to interact with other people and with other ideas, with your experiences, and they go into what you think the probability is. And that football captain who thinks that the probability of a quarter landing heads didn't invent that himself, nor did he check it out at home. He read it or somebody told him, and that's where that prior comes from. And that's all it is. The wave function's a prior. It doesn't do anything else. Then you measure it, and then you see. Okay. So what cubism suggests is that quantum mechanics should be reformulated in terms of probabilities, not spooky wave functions. And cubists actually are in the process of doing this. They are in the process of trying to write quantum mechanics in terms of probabilities, in terms of real numbers from 0 to 1, which is a lot easier to understand than the Bloch spheres, for example. And they're getting there, but there are mathematical problems with this. So anyway, the hope is that the resulting formalism will shed new light on what quantum mechanics is really trying to tell us about nature. A summary of what I've said is that the mathematical formalism of quantum mechanics right now is unaffected, so don't worry. Quantum probabilities are subjective measures of expectations for personal experiences. And I skipped the slide that shows that certainty is an opinion too. Even probability p equals 1 doesn't mean that something is real. It's just that I believe it very strongly. I would assign probability 1 that the sun will rise tomorrow, and I would bet all the way up to $1. The collapse of the wave function is an updating of a probability estimate. And finally, all physics is local. Let me end by, where are we? Wrong. Whoops. I just did something terrible. I don't know where I am. Sorry. Thank you. My wave function has collapsed just exactly at the right time. I was going to give you some references. Could you just get me back to where I was?
Yeah, I hope. So I say okay, but now you have to say share screen, and the one you want to share is this one. I hope. Yeah.
That's the beginning. You know, no, that's okay. I can go from there.
And you can go like.
No, I'll just go down.
Yeah.
There's a quick review of what I've said. That should get me there. One of the best bonuses of cubism is heuristic, meaning leads to new discoveries and inventions, and cubism has already succeeded in spurring new research both in pure mathematics and some in physics and even in engineering. And I wanted to give you some references. All these, the book you all have now, thanks to our generous host, but the original paper and the other two are publicly available in the archive. The first one is the original paper. It's very short. The David Merman's is a beautiful essay about with just words and no equations. And strangely enough, the new Wikipedia, which gets updated every now and then, the 2020 version under quantum Bayesianism is very good. It's very good. I recommend it, which is not true for all Wikipedia pages, but this one, and I didn't write it, by the way, but so I can recommend that. But anyway, that's where I want to end. Thank you.